Hello friends, welcome in lecture of fluid mechanics subject. Myself Mitesh Patel. I am an assistant professor in a mechanical department at a Dr. Subhash Technical Campus, Junagadh. Today's our lecture topic is a Venturimeter. So in this lecture we have seen what is the Venturimeter, what is the application of Venturimeter, where it is fixed. So let's start the lecture. First of all, what is the Venturimeter? So Venturimeter is a measuring instrument. It's measure the rate of discharge in a pipeline, and it is permanently fixed to the section of pipe to measure the discharge. Okay, when we have to measure into the pipe, that section we have to permanently fix the Venturimeter. Okay, the Venturimeter mainly consists of three parts: converging, throat and diverging. This portion figure is a converging part of Venturimeter. This portion of small diameter, this is a throat, and this section of Venturimeter is a divergent part. Okay, so Venturimeter is mainly consists of three parts: converging, throat and diverging. Okay, now types of Venturimeter. So Venturimeter is mainly classified according to in which position is placed into the pipe. So according to that, horizontal Venturimeter, vertical Venturimeter and inclined Venturimeter. So okay, now we have derived the equation of discharge or rate of flow for a Venturimeter. Okay, so first consider the Venturimeter is fitted in a horizontal pipe through which the fluid is flowing, as shown in figure. We can see from the figure the fluid is flowing through the Venturimeter and pipe is perfectly horizontal. Okay, now first we have considered the section 1 and section 2 at a throat and section 1 at a pipe. Okay, now D1 P1 is a diameter at a section 1, pressure at a section 1, and V1 is a velocity at a section 1, velocity of fluid at a section 1, and A1 is a cross section area of pipe at a section 1. Okay, now D2 P2 and V2 is a diameter, pressure and velocity at a section 2, area is a cross section area at a section 2. Okay, now we applying the Bernoulli's equation at a section 1 and section 2. So we know that the pressure energy, kinetic energy and potential energy at the both side of section. Okay, now the Venturimeter or pipe is perfectly horizontal, so potential energy difference is 0. So Z1 is equal to Z2 because the datum height at a section 1 and section 2 is equal. So Z1 is equal to Z2. So equation have only pressure, means pressure energy and kinetic energy only. Okay, now we have to find the value of pressure head, pressure difference head. Okay, so arrange in this way equation. So write the equation as this way. Okay, now we know that difference of pressure head is written as a small h according to figure. We see from the figure the difference in the pressure at a section 1 and section 2 is defined by the h. So difference of pressure head between a section 1 and section 2 is defined by the small h. Okay, so equation is written in form of small h is equal to V2 square upon 2G minus V1 square upon 2G. Okay. Now we are applying the continuity equation at a section 1 and section 2. So continuity equation is mentioned that A1 V1 is equal to A2 V2. Okay. So we get the value of V1 from the continuity equation. So V1 is equal to A2 V2 upon A1. Okay. Now put the value of V1 into this equation. So we can get this equation. Now V square upon 2G is take a common. So in bracket only 1 minus V2 A2 square upon A1 square remains. Okay. So equation is just modifies in this way. Now we get the value of V2 from small h equation. So V2 square is equal to 2GH A1 square upon A1 square minus A2 square. Okay. Now from both sides we can remove the square. So V2 is equal to under root 2GH A1 square upon A1 square minus A2 square. Okay. So this equation is V2 value. Now we know that the discharge equation is equal to A2 V2. Okay, at a section 2. So now we have a value of A2. This V2 value is put into this equation. Then we have find out the discharge from the Venturimeter. Okay, but this equation is theoretical equation. We have considered the ideal conditions. So actual discharge is lower than the theoretical discharge. So actual discharge is Q is equal to coefficient of discharge is multiplied by A1 V1. Sorry, A2 V2. Okay. So this actual equation is right in this way, and CD is a coefficient of discharge for a Venturimeter. Okay. Or we can say that coefficient of Venturimeter. Now value of H in the case of differential YouTube manometer, how we can find out? According to this equation, H is equal to X in bracket SH upon S0 minus 1. SH is a specific gravity of heavy liquid. SO is a specific gravity of liquid flowing through the pipe, means light liquid specific gravity. And X is a difference of heavier liquid column in YouTube. Okay. Now we see how the equation, this equation is get. If consider this YouTube manometer is fixed to the Venturimeter at a section 1 and section 2, which we are earlier considered. Okay. So section 1 have a higher pressure and section 2 have a lower pressure. So this condition is occurs into manometer. Now consider this datum plane and compare the both side of pressure head. Okay, liquid column head or pressure head. Okay, then from left side we can get the P1 plus column height pressure rho 1 G H1. Okay, and right side P2 plus light liquid column rho 1 G H2. Rho 1 is common for the both light liquid because the liquid is common which is flowing to the Venturimeter. Okay, so density is common for column 1 and column 2. Okay, so rho 1 GH2. Now the second column of mercury, so this pressure head for the column of mercury is a rho HgX. X is nothing but the difference of H1 minus H2. Okay. Now we have to find out the value of pressure head difference. So we convert the equation into P1 minus P2 and remaining is right side. Okay. Now rho 1g is take a common. So in bracket remains only H2 minus H1. Okay. Now multiply with the minus in this element. So sign of the H1 and H2 is differ. So here H1 minus H2, which is defined by the X. H1 minus H2 is defined by the X. Okay. So here we mention the X, H1 minus H2 instead of. Okay. So equation become P1 minus P2 is equal to minus rho 1 gx plus rho h gx. Okay. Now we can rearrange. So P1 minus P2 is equal to rho h gx minus rho 1 gx. Okay. Now gx is take a common. So in bracket rho h minus rho 1. Okay. Now in right side of equation we divide and multiply by the density of water as shown in equation. Okay. Now we know that density of heavy liquid to the ratio of density of heavy liquid to density of water, we know that it is a specific gravity of heavy liquid. Similarly, density of light liquid upon density of water ratio is specific gravity of light liquid. Okay. Now take a specific gravity of light liquid is a common from the bracket. So in bracket SH upon L, SL minus 1. Okay. Now we know that specific gravity of light liquid is equal to density of light liquid upon density of water. So density of liquid is equal to specific gravity of light liquid into density of water. So here we can write the density of light liquid. Okay. Now rho into g is moved to the left side. So write in this way. Okay. And here remains is a x in bracket SH upon SL minus 1. Now we know that the pressure head difference we can write instead of pressure head difference small h. So is equal to x in bracket SH upon SL minus 1. Here SH is a specific gravity of heavy liquid, it is a mercury, and SL is a light liquid, it is a water or any other liquid which is flow into the Venturimeter. Okay. So this equation is get from that. Okay. Now if the differential manometer contains the liquid is lighter than the liquid flowing to the pipe or Venturimeter, then we can say that the inverted manometer is used, then sign is different and equation become for H is find from this equation. Okay. This equation is also derived from the same conditions, but the U-tube manometer or differential U-tube manometer is inverted. Okay. Now we have solved the one examples for Venturimeter. So you can get the idea how the Venturimeter is used to what discharge find out. Okay. Let's take an example. A horizontal Venturimeter with an inlet and throat diameter. Inlet diameter is a 30 centimeter and throat diameter is a 5 centimeter. Okay. Respectively. Is used to measure the flow of water. Barabar? The reading of differential manometer connected to the inlet and the throat is 20 centimeter of mercury. Here YouTube differential manometer is used and reading of manometer is 20 centimeter. So it's defined by x. X value is 20 centimeter. Okay. Now determine the rate of flow. Take coefficient of discharge for a Venturimeter is 0.98. Okay. So we have write the data which are given. D1 means diameter at a section 1 30 centimeter. Area we can find out from the diameter at a section 1. Okay. D2 at a section 2. A2 means area at a section 2 we have find out, and D2 is given, so we find out the A2. Okay. Now CD is given. Now we know that the H is find out from the equation. H is equal to x SH upon SO minus 1. So we know that SH is a heavy liquid, specific gravity. So specific gravity of heavy liquid is a mercury. So specific gravity mercury, and SO is a specific gravity of flow liquid. So flow liquid is a water. So SO is a specific gravity of water and SH is a specific gravity of mercury. Okay. So we know that the value of specific gravity of mercury is a 13.6 and specific gravity of water is a 1. Okay. So we find out the value of H is a 252 centimeter. We know that the X is given 20 centimeter. So we can get the value of H in centimeter 252 centimeter. Okay. Now we know that the discharge equation of Venturimeter, Q is equal to CD A1 A2 upon under root A1 square minus A2 square into under root 2GH. So we have a value of all element in this equation. So we have a value of CD, area of at a section 1, area of at a section 2, and we also find out the value of H. So put the value of all elements and we have find out the value of discharge. Okay. Okay friends, I hope you all very well understand what is the Venturimeter, what is the application of Venturimeter, and how to measure the discharge from the Venturimeter. Okay. Thank you.